So how do you use this for factoring? So unitary x goes to gx. Mod n. So we're just multiplying by some g. So what are the eigenvalues of this? And suppose g to the r is congruent to 1, mod n. So g has order r. Eigenvalue, or an eigenvector, is sum g to the k e to the 2 pi I k L over r. Because what happens if you multiply this by g? Or rather, yeah, what happens if you apply the unitary? U times 1 over root r g to the k e to the 2 pi I k L over r is equal to 1 over root r. There's a sum here. Sum g to the k plus 1 e to the 2 pi I L over r is equal to well, so what we've done is we've replaced g to the k by g to the k plus 1. But you can get from g to the k plus 1 to g to the k by just rewriting the coefficients of the sum, rewriting the index of the sum, k equals 0 to r minus 1, making k prime to the pi I k over L. So I want to say you can take k prime equals k minus 1, and you get this is equal to e to the minus 2 pi I L over r c. So if you can estimate e to the minus 2 pi I L over r, you're done. And we can do that through phase estimation. Okay, So the question is, should I go into this step in more detail? Anyone? Yeah. Okay. Okay. So claim summation g to the k e to the 2 pi I k L over r is an eigenvector. Let's call it C sub L is an eigenvector. And the proof, well, okay, I want to divide this by 1 over root r. Proof is we apply u to it, C sub L, and we get 1 over root r sum g to the k e to the 2 pi I k L over g to the k plus 1. Because when we apply u to something, we multiply by g. So taking g to the k and multiplying it by g, you get g to the k plus 1. And now let's let k prime equals k minus 1. This is equal to 1 over root r sum. Well, I want to say it's the same sum as before. because k equals 0 to r minus 1. We now get k prime equals 0 to r, k prime equals minus 1 to r minus 2, but g to the k plus 1, but g to the 0 is equal to g to the r, so we can use the same limits on the summation. G to the k, we replace k plus 1 by k, e to the 2 pi I k prime minus 1 L over R. So this is the same as this, except we've multiplied by e to the 2 pi I L over R equals e to the minus 2 pi I L over R times our eigenvector. So these are the eigenvectors of the transformation x goes to gx mod n. Now, there's one last step, which is I assumed that we had a Unitarian eigenvector. We don't actually have the eigenvector. If we had the eigenvector, we would know how to factor. But suppose what we could do is we could pick a random eigenvector and then apply this. That would work. So how do we pick a random eigenvector? Well, that involves density matrices, which I am going to talk to you about the first class after the exam. So the first class after the exam, I will show you how you can, well, maybe not actually pick a random eigenvector, but do something entirely equivalent to picking a random eigenvector. And then that will give you Kitaev's algorithm for factoring by phase estimation. Right. So, yeah, and the last thing I should have said is once you know R, you do exactly the same thing, continued fractions, as you saw last time.